Hello, this is Brian Washburn. I like to talk about the motion of rigid bodies. And so let me first define what a rigid body is. Here I have a rigid body basically consists of some object. Here I kind of have a picture of it. And that object consists of a bunch of little masses, m sub alpha. Okay, and really the definition for a rigid body is for that rigid body, I have an m alpha. But I have also somewhere else a m beta. A rigid body is defined as the distance between the two, m alpha and m beta. So basically this distance right here, it doesn't change as the object rotates. That's the definition of a rigid body. Now in engineering physics 1, because of that, we could always show that the motion of a rigid body is equal to motion of the center of mass plus rotations about the center mass. This was a big result of in engineering physics 1. And so it's important at this point to define the center of mass. So if we take a look at a picture here, r alpha is a position vector from a fixed coordinate system to the m alpha particle. And then I can define a position vector called the center of mass, big R, and that's going to be equal to the sum over all the alphas, m alpha, r alpha, divided by the sum over all alphas, m alpha. That's the total mass. So that's going to give me a point in space that represents the center of mass of the system. Now, what's going to be really important is to, in the end, I'm not going to care so much about the fixed coordinate system. I'm going to put a coordinate system at the center of mass. So at this point, it's useful to define a relative position vector from the center of mass to m sub alpha. That relative position vector, we're going to call that r alpha prime. And that's going to be equal to, well, you can see here, it's just going to be the difference of r alpha minus big R. Okay. And again, r alpha prime is this little vector here. So this is the center of mass. This is alpha, and r alpha prime is a little vector that goes from the center mass to the m alpha particle. So what's going to be really important is to express derivatives not in a fixed frame, but in a frame that's kind of attached with the rigid body. But that means that frame rotates. And so what we have to do is we have to use our results from before to express kinetic energy and angular momentum in that rotating frame. And again, this idea of breaking up the motion of a rigid body into two motions, in the end, what we want to show is that the total, for example, like kinetic energy, the total kinetic energy is going to be the kinetic energy of motion of the center of mass plus kinetic energy of rotations about the center of mass. That's what we're going to show. Now in engineering physics language, we'd write this as 1/2 big M V, capital V squared, where V is the center of mass of speed, plus 1/2 I, where I is the moment inertia, omega squared, where that's the angular velocity of or angular speed in this case. So that's what I want to show going through all this. In engineering physics, we kind of said that and it made a lot of sense, but we never showed it. Okay, so how I'm going to show it? What I'm going to do is I'm going to look at rate of change of r alpha. Remember, r alpha is a position vector, but I want to look at that change in a reference frame that rotates with the rigid body itself. So that's the next thing I'm going to do. Okay, so again, what I'm going to do is I'm going to look at the rate of change of r alpha. Okay, at first I'm going to look at it in this fixed frame, and then from this I can show, from this, r alpha is going to be equal to r alpha prime plus big R. In the end, I want to do everything in a frame of reference attached to the body that rotates. That is a non-inertial frame, so I'm going to use what I learned before about non-inertial frames. But here, let's just express this. So just using this, the definition I just wrote down, that's the rate of change of the position, the center of mass position, and then the rate of change of the relative position with respect to the center mass, and it's all in the fixed frame. However, I want to do this in a rotating frame. Now this guy here, that is big V. That's the velocity of the center mass. And then this guy here, I'm just going to use what we learned before, or non-inertial reference frame. So this is going to be r alpha ddt r alpha prime, and that's in the rotating frame, plus omega cross r prime alpha. Okay, and that's using the result we derived for, for a non-inertial frame. However, r alpha prime, this term here is equal to 0 because the distances between the masses don't change. That's the definition of rigid body. So for a rigid body, I can show that rate of change of r dt in the fixed frame is just going to be equal to the center of mass plus this thing here. So automatically right here we show that, hey, we've broken down velocity in a fixed frame as a combination of center of mass motion plus rotations about the center of mass. Okay, so right from there we showed that. Okay, so now what we're going to do next is look at the kinetic energy using this result here. So let's do that next. Okay, so I have this result between the velocity in the fixed frame versus the velocity in a rotating frame. And in the end, now what I want to do is I want to look at kinetic energy. What I want to show is that the kinetic energy, the total kinetic energy is equal to kinetic energy center mass plus rotational stuff. That's what I want to show. So how am I going to do that? Well, I say the kinetic energy, again, I have a bunch of particles, so this is 1/2. I'm going to sum over all the particles alpha, m alpha, and then I have to do v squared. Well, v squared is v alpha dot v alpha. Okay, and what is v alpha? Well, that's this. This is v alpha. Okay, so now what I'm going to do is just stick that sucker in there. I'm going to get here m alpha, and then I have to be a little careful here. And the reason why I wrote it as a dot product, because I have to now take a dot product of this thing here. Okay, dotted. Again, that's a dot product with this thing here. And notice there's also a cross product in there. So it makes life interesting, but that's okay. We're going to handle it. So if you look at it, let's look at the first term. The first term, I'm going to get v dot v. Well, that's big m alpha. And let's just put a big bracket here. So I'm going to get v squared. Okay. Okay, that's cool. And then the other thing I'm going to get is I get a cross product term, a cross term, and that cross term is going to be 2 times v as a vector dot omega cross r alpha prime. Okay, we're going to look at that. And then finally, what I get is I get another term of omega cross alpha dotted with itself, and you got to be a little careful about this, that thing there. Now, again, that will be a scalar. Okay, that square really means a dot product with itself. Okay. Okay, so now let's look at those individual terms accordingly. Now the middle term, what's going to be there? So this guy here, this term here, notice I have v crossed with the v dotted with the cross product of this thing here. Okay. Now what you can do is let's look at that term a little bit carefully. So I have 2v dot with omega cross r alpha prime. What I can do is I can factor out. Well, I'm just going to use kind of a associative rule here, and I can say v dot omega. Okay. And then this is a little tricky here. Well, actually, let me not write it that way because that's not entirely correct. Okay, I gotta be a little careful with the dots and products and all this kind of stuff. So let me get rid of that. What I can show is by using a dot, I can bring. Actually, what I need to do is I need to sum over mass. Okay, that's because I have that 1/2 term, and then a half. Let me just look at the whole term by multiplying by 1/2 sum of m squares. Now what I can do is I can rewrite this as v, okay, and then bring that mass and all that stuff into the other part, dotted into omega, and then if I take this stuff here and put it there, that is just going to be the center of mass. Okay, so that's this. Okay. No, sorry, let's not write it. I have to write it completely. So I'm going to get omega cross, okay, mr. Okay, that is Okay, that's what I'm going to get there. All right. However, V. So this is, but V is going to be in the plane of, V is going to be perpendicular to this cross this. All right, and because since they're perpendicular, that means that cross term is equal to 0. That's actually nice. So then we can write the kinetic energy in the form 1/2 sum of alpha m alpha. Okay, so then what is this? So this thing here, okay, and then the remaining stuff looks like 1/2 sum of alpha m alpha omega cross r alpha. R of alpha prime. Okay, so again, we can identify a couple things. This thing here is the kinetic energy of the center of mass. This stuff here deals with rotations about this center mass. So this thing here must be equal to the rotational portion. However, at this point here, we do not remember what we really expected. Well, we expected this thing to look like, well, 1/2 I omega squared. So even though we were able to take the kinetic energy, break it up into rotational portions and that of center mass, we don't have the moment of inertia just yet. Okay, and we can easily get there. Well, actually, it's not that easy, but we can get there. And I'm actually not going to do it here. I'm going to do this in class. But what we're going to show in class is we can take this rotational term. And what can we do with this rotational term? Well, what we can do is you can express this rotational term in terms of something you recognize as the center, the moment of inertia. And so what we're going to show in class is that I can write that exact term. Okay, remember, these are vectors. These are vectors in 3 dimensions. Okay. Oh, I forgot. So one thing I forgot is the square. And remember, so you got to be careful here. This is omega cross r prime alpha. That's a vector. And then the square means I dot it to itself. So that gives me a scalar. Remember, kinetic energy is a scalar quantity. Okay. So what I can show, and I'm going to show this in class, and this is also done in the book, is that I can represent basically this term here. Again, let me rewrite it. The rotational term looks like 1/2 sum alpha m alpha, and then I'm going to get omega cross r alpha prime squared or dotted with itself. What I'm going to show in class is I can rewrite this as a new sum. Okay, where I sum over the elements. Okay, so I want, again, really what I want to do is I want to write that in terms of something you recognize as the moment of inertia. All right, and what I'm going to show is that this sucker here can be written as a sum over I and j, where I and j go from 1, 2, 3. So those are the 3 coordinates. I can rewrite this sum as a sum of something called the moment of inertia, ij. Okay, omega j, omega j. All right. Now, you may say, well, okay, what the heck is that? Well, that is the thing that we recognize as the moment of inertia. However, notice that it has, not one indice, it has 2 indices. So this moment of inertia really represents for 3 dimensions, something that has 1, 2, 3 elements, a 3 by 3 element like this. Okay, well, that's a matrix. And so this thing here, we don't call this just the moment of inertia, we call it the moment of inertia tensor. This is a generalization of the moment of inertia that you learned in engineering physics, and we'll explain a little bit what that means. Okay, now what are these guys, omega I, omega j? Well, omega goes from omega 1, omega 2, omega 3. Those are the components. So if omega is a vector, an angular velocity, it has 3 components in 3 space. Okay. Now, since I have this moment of inertia tensor as a matrix, the natural thing is not to write this as a sum, but to write this as a matrix product. So that's what we're going to do. So we can identify that we can write this thing here as a product of omega I omega. Okay, now let me explain what these are. Omega is a column vector with all the components of the angular velocity 1, 2, 3 like this. I, and I'm going to use this kind of scripty I to denote that this thing is a matrix element. Okay, it's a matrix where again, let me just write it out just to be really anal about it. Okay, again, I have I11, I12, I13, I21, I22, I23, I33, I31, I32, I33. Okay, and we can write a more general relationship to get those moment of inertia components. And let me write that expression. So again, if I want to actually calculate those guys, I have to actually do an integral. Ij is going to be equal to, well, let me write it in terms of a summation, and then I'll write the integral for m alpha. Okay, so then we're going to show that that's going to be equal to, so I'll explain what that is. That is called a Kronecker delta function, sum over, that is the sum over k of x of alpha k. So that is the x component, y component, z component of k. We sum over 3 here, minus xi xj. Okay. And then that's the discrete form, and if we want to get a continuous form, which is actually what we're really interested in, and instead of doing a sum, what I do is I integrate over the volume times the density of the thing, and then what I have here is I have the delta Kronecker delta function sum over k over 3 x instead of calling alpha, it's just we're just calling x squared. Sorry, there should be a square there, minus xi. Okay. Hey, this is all in the book. I mean, you guys can read this too, but okay. So that's how I get the moment of inertia terms. Okay. Now there's a new kind of symbol here, kind of Kronecker delta function. It's kind of a cool symbol. What it does is it's kind of like a discrete form of the delta Dirac function, and all it means is delta ij is going to be equal to 0 if I doesn't equal j, and 1 if I equals j. Okay, that's a moment of inertia. Now, that's not what you learned in engineering physics 1. I mean, it's like, what the heck is that? I mean, I only learned the moment of inertia. But actually you did, and we just lied to you about it. And so let me explain, what the heck that moment of inertia. Remember, I got this 3x3 matrix. What the heck does all this stuff mean? So let me explain. Let me try to draw here. So I have to draw a tennis racket. Tennis racket's kind of a cool thing. Okay, so here's a tennis racket. Okay, and I'm going to draw a coordinate system. So I'm going to draw x, let's call this z, x, and then I'm going to put y along the axis of the tennis racket. Now, there are 3 ways to flip this tennis racket. Okay, one way of flipping it is to rotate along, say, the z direction. Okay, so if I rotate along the z-axis, okay, and there's a moment of inertia associated with that. I'm going to call that ixx. And so back to my my moment of inertia tensor. Okay, I as a matrix, ixx is going to just be the moment of inertia rotations about that. Then also there's also rotations around the y direction. Now you can see that there's a different distribution of mass along that axis. So I expect a different moment of inertia. Okay. And so what is that term? That term is going to be Iyy. Okay. And then finally we have rotations among the z-axis as well, like that. Okay. Well, you can see that's going to be that might be different too for a given object. And so I'm going to call this zz. So all those different rotations correspond to elements along the diagonal. Now, because of symmetry, then I have these other elements. For example, I have element x, y, and then here I have element yx. All right, those guys are going to be equal to each other actually because of symmetry. So and you can see that from the expression. You can see easily from the expression that those are going to be equal to each other. So all the off-diagonal elements are going to be kind of equal to each other. So xy is equal to yx, xz is going to be equal to izx, and then yz is going to be equal to izy. Just from symmetry, you can see that. So that fills out the matrices. Now, if you just pick a coordinate system, arbitrary coordinate system, you're going to find that for a given object, so you just arbitrary check a coordinate system, you're going to find that the elements of the moment of inertia tensor are not all going to be 0. But however, if you're smart, you can pick a coordinate system that makes all the elements 0. Okay, and those elements are called the principal components for a given system. And it's pretty easy just by looking at symmetry to guess what those are. Now, say you can't do that. Okay, say you can't do that. Okay, and you can't find these principal axes. You can always find them by diagonalizing a matrix, and that's what we did. That's what we've been doing all along. So if I have a matrix A, and I want to create a diagonalized form of that, how do I do that? I solve an eigenvalue problem. Okay, and that's how we're going to diagonalize a matrix. So if I give you an arbitrary matrix, you always go to the math max. Now, for physics, we're lucky. What we can do is we can look at an object and say, here's some symmetry. We can pick the coordinate system, and then based on that symmetry, we're going to show that the off-diagonal elements are going to be equal to 0. All right. Now, why do we want to even work with things that are off diagonal? Okay, well, the reason why is because when we do the matrix multiplication, it's going to be a heck of a lot easier. Remember, T is going to be equal to the rotational omega cross omega I omega. Okay, so what does that look like? Let's write it out. Really, it's going to equal to 1/2 omega 1, omega 2, omega 3. And then I do a matrix multiplication here, and then I have a column vector here. That's what that looks like. Now, if I just have elements here, here, and here, and 0 everywhere, that's a diagonal matrix. That's going to make this matrix multiplication a lot easier to do than if I have a bunch of elements. Okay, so diagonalizing the matrices is again going to make things a lot simpler. In the end, we're going to get equations of motion, and that's just going to make life a lot simpler. Okay, so we finally have, through an expression, we now have an expression for kinetic energy. Kinetic energy is going to be equal to 1/2, in using our matrix notation, which is the best way to do it, omega I omega. And that, again, back into my EP-like language, we wrote this thing here. Okay, but again, life is not as easy as EP. All right. What about angular momentum? Well, angular momentum, okay, well, going back to what you should have learned in engineering physics, angular momentum is equal to L, L is equal to I times omega. Well, here, what we can show is that, or obviously you can see, that's going to be equal to I omega. So let's write that as vectors like this, okay? And again, what does that look like? Well, L is a column vector, L1, L2, L3, okay, it's a vector, and that's going to be equal to I, which is a 3×3 matrix, omega 1, omega 2, omega 3. Again, this is why you have to know how to multiply matrices. And again, you can see if I have a diagonal matrix for here, that makes the matrix multiplication a lot simpler to do. Okay, so you can see that, you know, because rigid bodies inherently are three-dimensional objects, okay, we have to use basically kind of a tensor algebra, matrix algebra, to express these common physical quantities that we know, okay, in a general thing. In engineering physics, we kind of did it and kind of looked at the most simplest cases. All right, well, you're not so fortunate anymore, okay? This is real life stuff, so the life isn't easy, so this is what we have to deal with. However, it's not that bad. In the end, we can express things as matrix multiplications, which isn't that bad to do. All right, and so we're going to do problems, and when we do problems, we're going to have to do some matrix multiplications to get the equations of motion. So we'll do that next time. We'll talk to you later. Bye-bye.